Hello, this video is for Unit 7 Biomechanics in Sport and Exercise Science. We are looking at B2 reaction forces, which is part of 7.2, the assignment all about forces. So hopefully you remember that Newton's third law of motion suggests that for every action force applied, there is an equal and opposite reaction force. So this skateboarder throws a ball, applies a force to that ball, and the ball applies an equal and opposite force backwards. So the action force is the force on the ball, the reaction force is applied back on this skateboarder's hands. Of course, if this was a larger bowling ball, you'd require a bigger force, but you would have a bigger force applied back on you. But the principle is there. For every force applied, there is a contact force applied. There is an equal and opposite reaction force applied. So in this system, this swimmer pushing against the wall of the swimming pool, they apply a force on the wall, and we can tell by the length of the arrow, the size of the force, the magnitude of the force, they get an equal and opposite force applied from the wall, i.e. the blue arrow propelling, which the athlete used to propel themselves and accelerate them off the wall into their swimming their length. Similarly, let's have a look at this example. So where have we got action and reaction forces? So the batter strikes the ball, applies an action force onto the ball, and the ball applies an equal and opposite reaction force backwards. Obviously, the mass of the bat and the momentum of the bat outweighs the ball's, and the ball shoots off. Similarly, when they plant their foot onto the ground, that's an action force contacting the ground, and the ground applies an equal and opposite reaction force backwards. So let's get some facts down on what reaction forces are. So they are, or reaction force is, a support force exerted upon an object. This is in contact with another object. So it's this reciprocal force. We've got an action force and we've got a reaction force. Action forces are imparted on an object by another object. So we impart a force on the ball, or the shot put in this case. The shot put imparts a reaction force, which is equal and opposite, back on our hand. We apply an action force from our foot onto the ball, and the ball applies an equal and opposite reaction force back onto our foot. We apply an action force on the block, and the block applies an equal and opposite reaction force back onto the swimmer to enable them to dive. Okay, so we've got these equal and opposite action and reaction forces. But in all of these examples, why is it that both of those objects don't move? Why is it the shot put moves, the ball moves, the diver moves? Well, the answer is because the ball, the football, the shot put, sorry, the football and the diver have a relatively small mass compared to the other object. The other object in the shot put example is the athlete. The ball's other object is the athlete, and the swimmer's other object is the block, which is connected to the floor, which is connected to the earth. So in these examples, the object is propelled, the athlete or the balls are propelled because the other mass is relatively large and stable. So a really critical or relevant reaction force that you need to give detail about in your work is ground reaction force. And logically, this is the reaction force that the ground imparts upon us as objects, particularly in order to run or jump. You know, we apply forces to the ground apply forces equal and opposite direction back on us. So how much ground reaction force there is dependent on the object's mass and gravity acting down through that mass, i.e. its weight. Sometimes, however, we add additional muscular force. We push down on the ground. So the example on the right here is actually just of an athlete stood on the ground. So it's just their weight. Gravity acts through the object's centre of mass and is a force applied down through these 2 points of contact. So weight is divided equally in this case between both feet. You can see by the length of the arrows, they are equal in length. The total weight is the sum of those 2 arrows. The ground reaction force is so that's the action force. The ground reaction force is the equal and opposite force applied by the ground back up through the athlete's feet, and it's got to be equal, and you should just about see that the arrows in both cases are equal. So this is somebody stood still. This is purely the downward force of weight through both feet and the upward ground reaction force up through both feet. These upward and downward forces are equal. And those bits of information just summarise what I've explained to you. Obviously, if this was a larger massed athlete, these arrows would be a bit longer, as would these ground reaction force arrows be a bit longer, because it's mass, it's gravity acting down through mass. If there's a bigger mass, there's a greater weight. I think it's key to note that these forces, reaction forces, are contact forces, so that they are applied where the feet contact the ground, where the ground contact the feet. Now, what's different about ground reaction force when we want to jump and take off from the ground? So firstly, we don't just stand there. What we do is we bend our knees, we do almost like a squat, and we push down on the ground. So not only have we got our weight acting downwards, we've got additional muscular force acting downwards as well. And that it creates a greater downward force, which means, of course, that in response and in reaction to that downward force, there will be an equal and opposite, and therefore larger ground reaction force acting back on the athlete. And ultimately, the athlete would take off. I haven't got it, can't show it on this diagram, but the athlete would take off. So again, why is it that we move and the ground doesn't move? Because the ground represents, the earth represents this massive, huge, ridiculously large mass. We can't move it, it moves us. But whatever force we apply to it, there's an equal and opposite force back from it. So let's take a moment to study these graphs. These are ground reaction force graphs, and they show a couple of different types of ground reaction forces. So forget the diagrams for a minute over here, the images. Let's just look at the graphs and identify what they're showing us. So these all 3 graphs show a reaction force from a foot placement on the ground. However, the bottom one here, which is probably least relevant, shows mediolateral forces, side-to-side forces when you put your foot down. Now that's not particularly relevant in a straight line sprint. Maybe on a bend on a 200 meters or 400 meters, there may show more variation in those forces, but I would for the moment ignore that one. Then we've got this middle one. So this middle one shows anterior posterior forces. This is anterior posterior means front to back. So if you push back on the ground pushes forward on you. So anterior posterior is that sort of front to back applied force. And that will have relevance to us in particular phases of a race. And the top graph here shows, as it says, vertical forces, up-down forces. So these are, again, quite relevant for us at different stages of our event. Now, let's look at the anterior-posterior one first. First of all, identify that in the block, when you're pushing out of the block, the front-to-back force is biggest. So these are the strides that you're taking when you're leaving the block. And the further you get away from the block, you can see the red line shows this sort of downward trajectory. So early on in those first few strides, you're pushing backwards more, and the ground reaction force is pushing you forwards more. But as you get further down the track, that back to front, backwards forwards pushing force, ground reaction force, decreases. Now, why is that? If you've watched a sprint event, for example, you'll see that as they leave the blocks, they are leaning forward a lot, and the first sort of 20-30 meters, they remain in a fairly low forward position. So that accounts for the pushing back and the ground reaction force pushing forwards to propel you, to accelerate you out of the blocks. And as you get further away from the blocks, you become more upright, and therefore you lose that anterior-posterior drive. Conversely, the top graph shows this upward-downwards force. And what you can see is that from the blocks, there is a relatively low upward-downward force, but as we get further down the track, that upward-downward ground reaction force becomes larger. And that kind of makes sense, because once we've done our 20 to 30 meters acceleration, driving, keeping low, leaning forward, we become a more upright position, and there's less forward backwards, there's a bit more upward downwards foot placement, a force going down a little bit more vertically, and the ground reaction force is a little bit more vertical. I'm not saying it's totally vertical, because it's not, or we would just bounce up and down. We've got to have some anterior posterior force to propel us forwards, but because of our body's position being more upright in the middle and end phase of the race, we get greater vertical ground reaction forces. So that's a lovely way, I think, of showing understanding of ground reaction forces, both anterior posterior and vertical upward downward. So high jump is another obvious example of how we have to generate a large ground reaction force. We apply our takeoff foot into the ground. Not only do we want it to send us up, but we want it to send us kind of over a bit, so horizontally a bit, so that we can travel up and over the bar. So we've got to generate a ground reaction force, obviously much larger than our downward weight force. So we push on the ground, we get an additional ground reaction force that allows us to take off and accelerate upwards. So again, I really like this example of a vertical jump. And this is actually a graph that shows force measured. So this is a scale of ground reaction force on a force plate. A force plate is a very specialized scale, basically, that sits in the floor of a biomechanics lab. If you stand on it, you get this. This is essentially is the ground reaction force of your weight, just you standing still. But it also shows us jumping and taking off and landing. So this is all the measures of the ground reaction force as we do that. So the first couple of seconds are essentially the athlete stood still on the force plate. Then there's a decrease in reaction force, ground reaction force. Why is that? The reason that we have that decrease is because the first thing we do when we prepare to jump is we unweight, we bend our knees, we start to move downwards, we become a little bit weightless for a moment, almost like when the lift starts to go down and you've got that little moment when you're unweighted. But what we then have to do is stop ourselves on the downward phase. So even though the force is getting bigger, this is the bottom of the downward movement of a jump. We've got to almost like put on the brakes to stop ourselves smushing into the floor. So we increase the force we push onto the ground to stop ourselves, to brake ourselves. So between about 215 and 235, we are increasing ground reaction force because we are pushing on the ground to brake us, as in to stop us, to slow us down. Because we then got to change direction and go push ourselves, propel ourselves upwards. And so this sort of upward bit here is the ground reaction force as we push ourselves off the floor. Now this peak here, which is about 2,000 newtons, this is the peak ground reaction force. That is not when we take off though. We've actually got this little bit of dip just before we take off, when there's no measure of force on the force plate. Clearly we're in the air. So why is it that the ground reaction force decreases a little bit just before we take off? Well, between here and the takeoff point, we are gradually leaving the floor and unweighting again. So we're reducing how much we're pressing on the floor, and therefore how much ground reaction force there is. So we go unweight, brake, push to accelerate upwards, take off a bit, take off totally, no ground reaction force because we're in the air, so there's no contact with the ground, and then of course this huge ground reaction force is when we land and we have to rapidly decelerate. If you think about it, gravity is accelerating us down to the ground, so we pick up momentum downwards and we've got to brake and stop ourselves again, sort of smushing into the ground. And there we are, we settle down back to normal. So there's a lovely way of showing the different phases of a vertical jump. So here's again a more visual representation of that very same graph. For starters, here's a force plate. It's this sunk into the floor of the biomechanics lab. We've got our stationary position, our unweighting, our braking ourselves on the downward phase. So up to this point here, we're still going downwards. Then we start pushing to push ourselves and propel ourselves upwards. Then we take off, and then we land. And I've got a little video that shows the actual jump and this graph in action.
What is it? Think of force plates as a bathroom scale, very expensive bathroom scale. This expensive, sophisticated scale can precisely measure fluctuations in weight or force on tiny time scales, often measuring 1,000 times per second. When we look at the graph, we can divide it into several phases. First, there's the weighing phase. This is the quiet period, where the athlete stands still so we can measure their body weight. Next is the unweighting phase. This begins at the onset of movement when the athlete descends by flexing their lower limbs. The phase extends until force is equal to the athlete's body weight. This endpoint coincides with maximum negative or downward velocity. The braking phase begins as the athlete nears the bottom of the squatting movement. The athlete is braking or decelerating during their descent en route to moving back upward. It's sometimes referred to as the eccentric phase, describing the theoretical muscle action during this time frame. The phase ends at the bottom point of their squatting movement. The propulsion phase begins when the athlete's center of mass begins moving upward, and it continues until takeoff. The flight phase spans from takeoff to touchdown. There's no weight on the force plate, so it reads 0. The last phase is the landing phase. At touchdown, the athlete generates force to slow down their velocity by bending their lower limbs. This phase ends at the bottom of the squat, where the center of mass velocity is 0. There are lots of ways we can use the information from a force plate, including how to very accurately calculate our jump height.
So a really detailed analysis of ground reaction force. We use this in long jump, we use this in high jump, we use it in basketball and football to jump for a header. We push on the ground, it pushes back on us and allows us to propel ourselves into the air for whatever purpose we're after. So there we have reaction forces, ground reaction force given in a lot of detail, variety of examples of action and reaction forces and how we produce forces within our sports activities.